So, good evening, all. We should start today's live session 11. So, myself, Ashok Kumar, PMR Scholars, and I will take your doubt and some basic concept of that flexible MEMS based and CAD design tools inventors in these sessions. Uh, so, first, we will take your doubts regarding the lectures 11, class 11s. So you can unmute yourself and you can ask me your doubts regarding that from that week 1 to week 11 if you have any doubt regarding the course, regarding the assignment, quiz, or any basic doubt that subject related doubt. Then we will move forward. So you can unmute yourself and you can ask your doubts because it is the discussion class. So I need your participations also. Okay, so if you have no doubts, so we will have some questions. So
Um,
before
Good evening,
taking, yes,
sir. I have one doubt related to baking. So, sir, what is the need of soft baking, sir?
what can you speak again? That voice
Um,
will be
yes, sir. So, my question is, what is the need of soft baking?
soft baking.
Yes, sir.
Okay, during the like that when we have to do the lithography. Okay,
Uh, yes, sir.
like that. See that this is my substrate, and I have coating photoresist here.
Okay.
Okay,
Yeah.
and photoresist in the form of the liquid. Okay,
Yes, sir.
or it have some high viscosity of that solution have the high viscosity. So when we have to draw cast it have the photoresist like that suppose that SU8 or PMMA is a type of photoresist. Okay, so
Yes, sir.
during that when we have to drop cast or during the spin coating it will be remain in the form of the liquid and it will be uniformly coating, so we have to do the soft baking around to 40 to 45 degree to make it hard to remove any solvent that will be evaporate during the heating that.
Okay, sir.
Okay, some water molecules will be remain on that surface and we cannot expose UV light during in the liquid form that photoresist.
Okay.
And for adhesiveness of that photoresist to the substrate we require the soft baking in that form also.
Okay, sir.
Okay,
Yes, sir. So, sir, can't we do directly hard baking, sir?
no, hard baking is doing after that exposing the light.
Okay, okay, sir.
It is the after the exposure of light we do the hard baking.
Yeah, sure.
Okay,
Yeah.
so it is the standard process you have to follow during that photolithography.
Okay, sir.
Okay.
Yes.
Anything else?
No, sir.
So this is the some diagram of that flexible MEMS. So MEMS in the flexible substrate can be defined as a micro electromechanical device and system embedded in the flexible polymer or plastic film such that device is conformed to non-planar surface and object. So in case like that we have before that we design the MEMS based devices on the either silicon substrate, glass, sapphire substrate. So in that case of the flexible MEMS, we take the substrate as a flexible type, which is either in the form of the polymer or the plastic film. So these are the two diagram that you can see that it can be bent. We can bend that substrate in any radius. So it after removing the bending, it will remain in the same form. That is the advantage of the flexible. Okay, like that. uh, like that this is the my substrate, like that this is the polymer substrate, and I have made the devices on this substrate. When I bend this when I bend this substrate like that, this is the bending of my substrate. So and after bending I will again remove it, it will be come into the its original form, and nothing my network is post.
Yes, sir. You are audible, sir.
Actually recording will be okay. So what will happen? So it will be remain in the original form. No, nothing. It will be after the bending. The property of that devices will be remain the same. This is the our aim to design or to develop a device on the flexible substrate which give the same response or same property after bending, folding, or anything. Like the people are using the cloth as a substrate for develop the device on the cloth paper, or some paper, or people are developing the like that MOSFET and CMOS or BGT or diode, they are developing on the paper also. Okay, and they use the organic material. So sometimes people are working on the organic field effect transistors, organic MEMS, or you can use the metal oxide also, that inorganic compound for that flexible devices that. So this is the flexible organic electronics summary. Why organic? We will not looking on the organic. We are main focus on that flexible. So semiconductor material is polycrystalline silicon. That process temperature should be 600 degrees Celsius, and mobility is around 50 centimeter per square. And hydrogen generated like that SiO2 vapor, that processing temperature is around 300 degrees, and that and organic semiconductor like polymers, and these polymers, and that even we can operate at room temperature 100 degrees Celsius, but it has a disadvantage is that with very low carrier mobility is that. But the operating temperature is room temperatures, and many more devices that we require to operate on room temperature, not at high temperatures. So it is the advantage of that flexible. This is the circuit applications, like that we can make the organic light emitting diode. These pictures I have taken that advanced functional materials, that is the references. So you can design a OLD, lasers, CMOS, BGT, diode, whatever that component you want, electronics component you want to fabricate, you can fabricate on the flexible substrate also that. So this is the system application of the flexible devices. So application from smart system to IoT. So component of the smart system sensing input, like that our touch screen of that phone, and it should be the flexible phone. It will be foldable phone. We require now that for phone, cell phone, mobile phone will become with the foldable screen. So that touch sensor we fabricated on that flexible substrate. Process storage, driving output, power supply, wearable. So this is the wearable. We can wear the devices on our hand. Robotics in that component, energy harvesting, like that hydrogen, and that in that things, communications in the 5G 6G communication, portable devices, like that cell phone, watch, a tablet, a computer, laptop, that will be that in that case. So this is the things we can do through the flexible electronics. So this is the flexible electrodes. This is the pressure sensors people have designed through the flexible sensors. So we have the this is that PDMS is a substrate they have used. Then they deposit the copper electrode. This is the copper electrode, and above that they again deposit the they have again deposit the PVDF and RGO as nanofiber as a sensing layer, and then again the PDMS, and then they have press on that sensor like that. This is the pressure sensors. So this is the array. That the array means there is a lot of devices, around 10 to 20 or to 40 to 100 devices on the same substrate will be designed. That is a means array. And this is the why like that we have to press, and okay, that message will become that press. So as a touch screen, when we have to press on somewhere something on that like that, we want to press the one on a touch screen. When we have to do press, that pressure sensor will sense that input on one, and that give the output that one will be pressed. So it will give the command to the system that you have to operate as a the command to one, that one will be pressed by the user. So you have to go that whatever the one will be put, that message will display on the screen of the devices. So this is the printed electronics of the flexible electronics. So printed can be much faster process compared to the conventional inexpensive process like that newspaper. We can print the newspaper. Inkjet felt printing process may be also enable like that. We can manufacture RFID tag, e-paper, disposable electronics. So these are the example of that devices that application of printed electronics. So these are the materials for printing electronics we required. What are the materials for flexible electronics? Silver, gold, nickel, transparent oxide semiconductor, CNT nanowire, conductive semiconductor polymer, nanoparticles, quantum dots. You can use as per your application requirement of your devices. So what type of the sensor you want to fabricate, and what type of that materials you want to use, that which give the good response or the good resolutions of your devices, according to that you choose the materials. So this is the expectations of all printed transistors, that this is the printable semiconductor, that printable conductor like source, drain, gate, contact, polynative, PDS. These are all the materials we use as a conductors. These are printable semiconductors, tips, pentacene, polythopines, P3ST, PQ212, CNT nanowires. These are the semiconductor materials. So we use the substrate. So these are the insulator. You use the PMMA, polyimide, spin on glass, PVP, epoxy, that SU8 as a substrate, as a insulator for to dial to like get like that. In a conventional we use insulator as a SiO2 as a insulator, or to insulate the gate. In a CMOS technology we use the silicon nitride as a insulators, but in case of that flexible, we use these materials as a insulator. And substrate, polyester, PES, polyimide, pan, paper, foil, whatever the substrate you can use. Okay, even you can use as a substrate like that tree leaves also you can use that substrate, cloth. Okay, and these are the source and drain, and we use the organic semiconductor materials here. So, what is the difference between the flexible and printed electronics? Flexible, a key enable for the IoT as a part of the Industry 4.0. So, Industry 4.0 is the standard. It is uh, the standard will be made by the government of India, and some industry regulations that now offer unique mechanical flexibility and functionality and low cost, offer the creation of the intelligent lightweight electronics, possibility of the printed by simple uh, printed process, integrate into new way to exploit its mechanical flexible form factors. Others synonyms that include plastic electronics, polymer electronics, large area electronics, thin film electronics, flexible electronics. These are the others name of that organic large area electronics. We use that flexible hybrid electronics also integrate with the flexible devices with the conventional silicon based devices. So we can make the hybrid structure or hybrid integration of the system in that case. These are the flexible and printed electronics. Next generation flexible and printed electronic systems. So what is the flexible systems? We have a display, AMOLED, computational, material development, integration growth in the healthcare, human interactivity, touch screen, haptic feedback, e-textiles, energy and storage. These are all the things we have can do that. So these are the type of the flexible and printed electronics. Mechanically flexibility, the thin substrate is mechanically flexible such that they can be molded, means we can here and here like that structure, we can bend it with any form like that, we can bend uh, we can bend to fit in the open even spaces like that. We can equally bend, we can unequally bend, uh, adhere to curvilinear surface, conformable, stretchable, and blendable and rollable. So all these are properties should be required for the flexible electronics. So we can use in any form, rough form, we can use that as substrate. So these are the conventional silicon-based devices that we have made a system or integrated system on silicon substrate. Then these are the flexible devices. These are the system integrated on the flexible, printed, and when the stretch. So skin-like or epidermal electronic systems. So wireless power coil. These are the wireless power coil antenna. These are the LED we have fabricated. Strain gauge sensor. We can temperature sensor we have fabricated. ECG, EMG monitors. These are sensors. RF diode, RF coil. So all the integrated. These all the sensors we can integrate it on screen. Base sensors. So you can see in this diagram that we have the wireless power coil, means wirelessly we can charge or supply the powers. We have the RF coil if the our work should be on the radio frequency based type, or we have to supply that magnetic field. We have the RF coil, RF diode. We have the strain gauge sensor here. We integrate the temperature sensor. We have integrated the ECG, EMG sensor. So in the medical form, we can design a sensor which can monitor the ECG or EMG, and its size should be 0.5 mm. So in the size of the only the 0.5 mm, we integrate all these small sensor on the one flexible devices. So this is the devices, transistor, LED, battery. We can fabricate it. We can fabricate the transistor. We can fabricate the LED. We can battery sensor on the flexible devices, on polymer, PDMS, plastic sheet, even cloth, papers, whatever the flexible things you can use, you can make the design on. So these are the flexible circuit, and these are the e-papers. So people are working on e-paper also, that flexible display, e-paper, RFID, solar cell, sensor, seat, lighting, all are now are moving on the flexible devices. From the conventional silicon, so people are working on the flexible devices more. That research work is going on the flexible things. So people are using the flexible substrate, and they use the semiconductor material, either organic or inorganic, as per their requirement of the devices and performance of the devices and applications. So these are a flexible and printed electronics, future system of the Internet things. There's a large area MN2 sensors array. So these are the electrode sheet. These are flexible on that fibers. They have monitoring that how medically that equipment, that future system of interest, they have supply and integrated their system. You can see in the diagram. Any questions still now? Any doubt? So these are the future system of the interest. Thin film batteries diagram is that actually diagram of the thin film battery. So this is the printed memory and electronics, and we can use one incubation layers and lamination layers to for safety of our environment protection and devices that in that case. Uh, these are the some challenges: complex system integrations, uh, 3 volt 6-bit analog to display converter, 1 to 8-bit microprocessor, and these are the challenges for high integrity of the component, high density of the component on this small substrate. It is very difficult. So these are the some questions answers. So I need your attentions. You should be your discussions, participation in their questions and answers. So if you have any doubt in regarding the flexible things, flexible component applications, you can unmute yourself and you can ask me your doubt first. I'm waiting for your. Okay, if you have no doubt, then we move forward. So first question is, whatever the spin coated on the silicon substrate during the fabrication of the flexible sensor designed for phenotyping tissue properties. So phenotyping tissue is a biological part. So you have to design a biological sensor on the flexible substrate. So what is the type of the substrate that I already explained in the one PPT, that PDMMS, polymers, uh, what is that? The substrate polysters, polyester sulfone, polyamide, pen, paper, foil. These are the flexible substrate we can use. So from that examples, so negative photoresist, you know that what is the application of that we can use for. Sorry, some network issue will be there, so I have disconnected. So negative, we will on that questions. So negative and positive both photoresist we use for transfer of the devices or that development of the devices or sensors. And PDMS is a substrate we use as a flexible. Okay, so why we use the PDMS? Next class is that PDMS. So PDMS is one of the most widely used polymer for fabricating microfluidic chip because of its external transparency. So it is a transparent. We can see from the naked eye that output to output that transparent is that, like that glass or IT coated IT coated substrate FTO. uh, Outstanding elasticity, so we can stretch and remove that, even we can stretch. Good thermal and oxidative stability, it will be stand at high temperature around 400 degrees Celsius and 500 degrees Celsius. Ease of the fabrication and seal with the various metal, so we can fabricate a device on that PDMS easily and seal with the various metal we can use. sorry, various materials for fabricating devices. So, full form of the PDMS is polydimethyl siloxane. Is a elastomeric polymer with interesting property or biomedical application. We use mainly for biomedical applications, including excellent resistance for biodegradation, biocompatibility, chemical stability, gas permeability, good mechanical property, excellent opticals, transparency, and simple fabricated by replica mounting. And these are that why we have used PDMS for biological things. So, any doubt? Anything else? So this complete the following statement. You have to complete this statement. In photolithography, when we use bright field mask and when there is a positive photoresist, the area which is not exposed to UV light. I already explained in the last 3 to 4 class that what is in case of the positive and negative photoresist. So in case of the positive photoresist like that, these are the positive photoresist we have deposit, and above we have like that these devices, these are positive photoresist. These are the devices we have made. Okay, so in case of the positive photoresist, what will happen after the developing? These will be remain. So what will happen? This area, unexposed area, will be removed. Okay, and what will be in the negative photoresist? This is a photoresist. Suppose these are the devices. So what is in the negative photoresist? These are the remaining. Okay, these and sorry. So these portions are remaining in the negative photoresist, and this will be removed in case of negative. So in a when we use a bright field mask and when there is a positive, they are not exposed to UV light, will be what will happen? Get stronger. Has no effect, get weaker. So the area which is not exposed to UV light, what will be happening there? That area will be not exposed to UV light. What will happen in that case? That area will be get
It's
harder.
strong.
Hello? Yes, Dr. Chandrasekhar.
Yes, it will get stronger.
Yes, yes. So what will when the light will be fall on that light due to the heating of light, it will be the photoresist will be more strong in that case, and it will be not easily soluble in the early solvent. So we can remove through the acetone and from heating that unwanted photoresist in that case. In case of the negative photoresist, it should be the opposite. It should be the weaker in that case. Okay, so both are the opposite. They have follow the rule of the opposition, vice versa. In case of the negative and positive photoresist. So next question is that strain gauge is a device that convert into. So what is the use of the strain gauge and what will be the application? What is the what should the strain gauge actually do? So which is the correct statement and why that?
Is right. It's a
Yeah.
passive device that converts. It's a passive device
Okay.
that converts mechanical displacement
Okay.
and leads to change of resistance.
Yes. So, Eastern gauge is a passive device because what is the meaning of the passive and active? Active means active and passive.
Passive is which is uh, I mean there is no any
Passive devices which require the external energy source for operating. Means we have to biasing with the external power supply. Active means it will generate its own active supply. Okay. So like the resistant, inductor, capacitors require the external power supply to operate. Like the transistors, op-amp, they are generating their own energy. They are the self-powered. So we have not to supply any in external power supply to that. Will be change in the mechanical displacement. What will happen? Like that, this is the instant gauge sensor. So like that, this is the resistant, and we have to make. So what will happen during that displacement? It will change the resistance. It will be move here and there, and change of the resistance will be measured at the output side. So we have like that. In the car we have the position sensors. So car will be move on the forward direction or reverse direction. So we have the instant gauge sensor in the car. So it will be measure that movement of displacement of the car either in the forward direction or reverse direction, and our sensor will be sense that directions, and it will be change in the resistance will be take place in that case when it will move upward in direction. So what will the resistance will be change in the take place? It will be display on the LED and OLED that your car will be move for around 10 meter, 100 kilometers or 200 kilometers through the instant gas sensor only. So these are the schematic of that that instant gas sensors. So these are the electrical wires leads. We have to supply that some external power supply, either 1 volt, 2 volt, 3 volt operating bias voltage. These are the electrode that is made of the gold, and these are the layers through which we get the eastern direction. So when we place something here and here, either it will be pressure sensors. So on that it will change the resistance between that eastern resistive force on that things. So these are the electrical equivalent electrical diagram of that eastern gas sensors. So these are that V out, V in, and these are the state direction that this 1 and 3, this is 4 and 2. So according to force or displacement, or whatever the applied of the pressures or force, we change in the resistance we can measure through the some. We have the two external resistance, and we can measure the two unknown resistance through that only.
sir, we can change the strain gauge from strain gauge actuator. Any actuator is there
Okay.
that can be activated with the
No,
help
no,
of strain gauge.
no. Instant we in the actuator, we actuator will be move here, and it will be one tip. Okay. It will also measure the resistance. Same actuator will be also working on the change in the resistance, but it will be based on the either the supply, not the pressures, light, and that anything that falls on tissue, and that deflection of that actuator, that tip will be take place in that case. But
So,
eastern gauge is same also, that is a tip, but it have the some value of the resistance will be changed in there electrode.
okay, due to the sensors can actuate the something which if more amount of force is placing over the strain gauge, so that can be reduced by using the actuator.
Yes, yes, we can do that.
We can do that, right? Okay,
Yes,
okay.
yes.
I mean, by help of any Bluetooth device that can be set up in the strain gauge.
Uh, Bluetooth devices, we can take that. What you want to take the data?
Yeah, it is data can be collected, and that same thing to be, again I wanted it to be like that has to actuate something, like the
Yes,
forces to be
you
reduced.
have like that. This is the like that. This is the sensors. This is the sensors. Okay.
Okay.
So you these output side you have to connected some electronics that IoT devices like that Arduino will be there. You have to see that Arduino. We take the output data of Arduino here. From Arduino we take that wireless transmitter here. So RFID like Bluetooth wire transmitter here, and again you have the wire transmitter, so you can transfer data through the wireless communications or Bluetooth.
Okay. Uh-huh,
So
uh-huh.
in between that you have to integrate with the system here, these sensors. So either through the Arduino you have to make a chip of that, and you can integrate that chip with the resistant, and you have to connect the wire through that microcontroller or microprocessor, and then you can take the through the wireless communication.
Okay. Okay, thank you. I'll in detail about it. I'll speak with you later. I mean,
Yeah, you
I'll
to,
mail
to
you.
like that in your ECG system, your data will be displayed on that some LED
Yeah.
or some OLD.
Yeah.
So inside that you have the one integrated circuit that will be there. That
Oh, actuator.
electronic circuit will be there. So what
Uh-huh.
will happen that like that you have to take that one probe will be touch on hand and one chest, and that everything you have to paste four probes like that during the
Yes.
ECG measurement.
Okay.
Okay. So two probe you have to put here to chest, and two probes at I think on the hand you have to measure that. Okay.
Yeah.
So one is the reference probe that will be select that we have to take the reference, and like that this is the four resistant you have to measure. Two resistant will become this probe from two resistant here.
Uh-huh.
My video will be not.
Here I.
Yeah. So two resistant will become from this probe, and two resistant will become from this probe. Okay. So
Okay.
this four output will be go to the some integrated circuit. He will be converted that resistant into some value, some graph that into that form, data form. So it will be coding in some Python, Java, and everything. That coding will be done by the some engineers. So it will be readable by that data to display on the LED.
Okay.
So you see that in the lecture 5, 6 that people are you if you go through the lecture that RPM motor will be controlled through the Arduino, that how they control the speed, rotation of that RPM motor, that IR sensors they have integrated with the Arduino. So this type of the this sensor you can integrate with the Arduino also that.
Okay. Okay. Thank you.
So why we use argon gas as in a PVD, that physical vapor deposition system sputtering process, or sputtering that RF magnetar sputtering system, atomic layer deposition systems, thermal evaporations. Why we use the argon as a gas for the creation of the plasma, or for that things? What is the reason why cannot use the night other gases, that oxygen, helium, hydrogen?
It is inert. Mainly, it
Yes, it
is
is there. So what will happen in that case?
like as it is told, unwanted reaction will not be there in the.
Yes, yes. Chemically inert, it will be not react with be any gases or
Yeah.
any particles there. So it
Yeah.
will not change the property of the material which you use for the deposition. Okay.
Mhm.
It
Mhm.
will just help to evaporate the materials or make the path that mean free path for that deposition of the atoms, and that
Okay.
hence prevents the surface oxidation or an unwanted reaction that to be occur. Yes, it right. Argon is a heavier molecules, and these facilitate faster surface modification. Yes. So molecule weight of the argon is higher than other gases. So it when the higher it will be make the direction to deposition. So more particle will be deposited on the surface. Argon is relatively cheaper with compared to the light noble gases. Other gases, yes, it will be more cheaper, less costly. We can use the nitrogen is also that source, but as compared to nitrogen, argon will be have more water weight molecules, so deposition rate will be faster in that case. So that So argon has a large atomic mass, inert chemistry, and relatively low cost. That's why we use in that case. Next question is, thermal and EB evaporation are chemically vapor deposition technique or not?
EB evaporation. Thermal and E-beam evaporation are not chemical vapor deposition. It is both. Thermal is thermal one. It's not a chemical one. E-beam is a light one. So both are not a chemical vapor deposition.
So have you seen that system in the science facility? I think you visited.
Yeah, I think I have seen. Not so remembered actually.
Okay.
It is,
So
isn't it?
yeah.
Okay. No, it is not a chemical vapor deposition, I feel.
Yes, yes. So in the thermal and E-beam, these are all the physical vapor deposition systems.
Physical
It
vapor,
is an
yes.
enclosed system, and they are working in the high vacuum. We require the high vacuum in the chambers, and we use the argon as a inert gas. Or in the E-beam, we use the electron beam. So electron beam also we make the argon as a flow. In that case, also that inert gas as a flow during the deposition of the E-beam and thermal. Chemical deposition system like that we have the tube one chemically that we have to use the heating zone like that this is a CVD the chemical vapor deposition system PCVD pressure CVD low LPCVD APCVD these are the chemical vapor deposition time system. So we have the one glass quartz tube in which we have to put some metals here and above that we have to put substrate and then we flow the gases here argon and inert gases through that and we have heating that material. Okay, around
Mhm.
8
Okay.
Celsius, 900,000 degrees Celsius, as per the melting and boiling point that material that we want to evaporate in that system. In that case of the thermal evaporation systems, we in the place of the heating we supply some current in that case. So we have the same boat like that. We have the some crucible, aluminum crucibles. We the put the materials here and we apply some current here. Okay, and during the current that crucible will be heat in that case, and it will evaporate the materials. In case of the E beam, we use the electron beam. Electron beam will be falls on the materials circularly. It will be generate an electromagnetic field inside that materials. Some ring will be generated inner or outside, and then it will be melt that material through the electron striking on that materials and evaporate in that case. So these both are the very costly systems in compared to the CVD, and it is the high stability and quality of the film in case of thermal and UV film is very good in compared to the chemical vapor deposition technique. But equipment cost is very high and maintenance cost is very high.
Okay.
So these are the some sensor like that stand for force, stand and tactile sensors. So the various method of the sensing force can be characterized as by balancing the unknown force against the gravitational force of the standard mass, by measuring the acceleration of the unknown mass to which the force is applied, by balancing the force against the electromagnetically developed force, by converting the force to the fluid pressure and measuring that pressures, by measuring the strength produced in the elastic member Young modulus. You can remember that in your physics you can calculate the Young modulus of the material elasticity of materials through which that strength will be produced due to the stretching of that materials through the force we have to apply on that case, and what type of the strength is the produced in the material you can calculate through the Young modulus in that case. So in most sensor, force is not directly converted into the electrical signal. Some intermediate steps are usually required. Thus, many forces sensor are the complex sensors. So we cannot force whatever the force we have to apply. Like the touch screen, we have applied our pressure or force some on touch screen. Like that, we want to dial some number 941427. So we applied on touch screen some force. So it will be converted into electrical signal and it will be go to the system and system will read that whatever the user will be pressure which number, and it will be display on that our OLD on LCD on the mobile phone. So this is the spring loaded force sensor with the LVDT diagram. So this is the force we have to apply, and this is the constant that constant spring constant of the materials that we have to press the spring, and this is the what change in the displacement or distance of that after applying the spring, that initially that spring in on that position, when we apply the press force on that spring will move on that direction. Okay.
Okay.
So compression displacement x, that whatever the displacement will be defined through the spring constant k. So x is equal to k into f. K is the spring constant, f is the force we have to apply. So with the linear range of the spring, the LVDT sensor produce voltage which is proportional to applied force. So we have to, these forces we have to convert it into voltage. So force is converted directly into form of the voltage, and we read that how much the voltage will change with the force. Suppose that I have applied 1 Newton per meter force on that spring, and I have received output side around 0.5 watt. So this is the when we can set this parameter. Then if you applied 1 Newton meter force, the change in the voltage is 0.5. If you apply the 2 Newton meter force, the change in 1 volt. So we can calibrate that sensor according to applied force and whatever the change in the output voltage we have received. So this is the strain gauge sensors. So strain gauge is a resistive elastic sensor which resistance is the function of the applied stress. So whatever the strain or stress we have applied on the sensors, it will be given in the form of a resistant. Previously in the LVDT, we give in the form of the voltage, force. But in case of the strain, we give in the form of the resistant. So the relationship is generally called the piezoresistive effect and is expressed through the sorry gauge factor SE of the conductor. So like the piezoelectric, last time I have explained the piezoresistive and piezoelectric effect in the last class in my video. So during that applying the pressures, the material is the piezoresistive materials. So that will be given when we apply the pressures in the output side. We given the change in the resistance, we can found that. So change in the resistance, that dr, that r is the standard resistance, dr in the change in the resistance is equal to SE into E. So SE is the gauge factor and E is the elasticity value of that sensor materials. So resistance of the metallic wire can be approximately linear equation, that R upon R net 1 plus X. So if we have to any like that, we have the gold wire or copper wire. So when we have to stretch, it will be change some forms in the resistance. It either will be reduced or it will be decreased in that case. Okay.
Okay.
Like that, rubber is the insulator. When we remove, when we stress or strain the rubber, it will its value will be changed, or length or width of the value will be changed in that case. And the resistant is resistant is equal to rho L by A. So either due to the length or area will be changed, or the resistance will be changed in that form of the material in that case. So where R naught is a resistant with no stress applied, that in the original form. So like that material at 50% of the copper and 43% of the nickel. So SC value of that gauge factor value is 2.0. Original resistance will be 100 degree. Resistance is 100. So SC is the constant over the range of the resistance for use under 200 degrees Celsius. And like that platinum alloy silicon, so gauge factor should be vary from that 4 to 6 of the temperature minus 100 to 150 degrees Celsius, and resistance should be at minus 100 degrees Celsius. If the we have the gauge factor is the 4, it is 50. If we have the gauge vector of the 6, it will be 200. And this total change in the resistance should be that 2160 to the 90,000 in that case. So this is the tactile sensors we use in the touch screen. We use the tactile sensors. 1 minute, please. Sorry. So
Okay.
touch and tactile sensor are devices, devices which measure the parameter of the contact between the sensor and object. So what this is the sensors and this is the contact. So what is the when we have to touch, what is the change in the resistance due to the touch or that contact between that screen and our finger? It will measure by the touch and tactile sensors.
Okay.
So this interaction obtained is confined to a small defined region. This contacts with the force and torque sensor that measure the total force being applied on the object. Okay. So an example is a touch screen on a mobile telephone is the tactile sensor we use on a mobile phone. So the tactile sensor loosely can be subdivided into three subgroups: touch sensors, spatial sensor, and sleep sensor. So what is the difference between the touch sensor? This is the detection and measurement of the contact force at a defined point, at a single point. Like that we have to press the one. So at a single point, what is the change in the resistance we can measure on the single point, like that. Now if we press the one, due to the force applied on the one, what is the change in resistance will be measured by the touch sensors. Another is a special sensors. It is the detection and measurement of the special distribution of force perpendicular to a predetermined sensor area and the subsequent interpretation of the spatial information. So it will take the some area like that, one centimeter by 1 centimeter, and whatever the force and pressure will be applied on whole area, it will be measured by the spatial sensor. Some area will be covered during that case. In the case of the sleep sensor, this is the measurement detection of the movement of the object relative to the sensor. This can be achieved either by specially designed sleep sensor or by the interpretation of the data from touch screen or tactile sensor. So it will take the average of that whole the area that touch screen we have to cover. So sleep sensor will be covered that what at what point we have to touch. It will take the average distance of all the force applied on different position of the touch screen, and average value will be displayed by the sleep sensors. So the desirable characteristic of the touch or tactile sensor suitable for the majority of the industrial applications. A touch sensor should ideally be single point contact through the sensor area can be any size. In practice, the area of the 1 to 2 mm square is considered as a satisfactory. So it should be given the resistant of the only at the one position. So we can the system will be read the accurate value. Otherwise, it will be if we place the one, maybe the system will be read the two if the area will be more in that case. So we take the minimum area of the 1 to 2 mm square in that case. So around that at 1 to 2 mm square area, how much the pressure will you measure? At which point it will be readable by that system only that. The sensitivity of the touch sensor is dependent on the number of the variables determined by the sensor's basic physical characteristics. In addition, the sensitivity depends upon the application, in particular in any physical barrier between the sensor and object. A sensitivity within the range of 0.4 to 10 newtons, together with an allowance for the accidental mechanical overload, is considered satisfactory for most industrial applications. So the sensors which we have fabricated, it's depend upon the variable physical parameter, that what is the sensitivity of the sensors, what is the power of consumption of their sensors, what is the response of their sensors, what is the resolution of that sensors, what is the standard deviation or error of that sensors, what is the applications we have to fabricate the sensors. And we if we design the touch screen sensors, it will be even measure the 10 newton of force can be measured by the sensor that. So when we apply the 10 newton force on that, the resistance will be equivalent to, will be readable by that sensor only that. So this is the applications of that sensors, touch sensors. These are the various examples where you use the touch sensor, instant gauge sensors, tactile sensors. These are the some diagram. This is the human mechanism, how human will be touched. this is a tactile sensor. You can see that that someone will be wearing in their finger, and someone touched their finger in this diagram, that how much the resistance. This is the array of the sensors that you can touch here. You can touch here like that. You can touch here, 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 here. So it will be readable that array, that these are the equivalent diagram of that sensors. So on off simple switch, resistive Western gauge type sensor, capacitive type sensors. You can use different type sensor for read of that touch pressures. So this is the membrane switch as a tactile sensors. So we use a one membrane as a substrate, and membrane have the flexibility that it will be when we have to do pressure, it will be pressed on that case. So these are the diagram that we have the multiplexers, the multiple input will become and we give the one output. So this is the schematic diagram of that things, and these are the real diagram that touch screen sensors. So you can see that how much the input will become here, and one is the output. So we use the and above the multiplexer here, and we got the one output side that. So we can 1, 2, 3. This is the keypad calculators diagram. So why we use the resistive in place of the inductive and capacity type of that strain gauge sensors or tactile sensor or touch screen sensors. So advantage, cost effective and low power requirement. Activated by any object, accurate value. What is the disadvantage of that? Polyester surface can be damaged. Only 75% is light transmission take place. Low endurance. 35 million touches. Accuracy will be low in case of that. This is the piezoelectric type of the tactile sensors. So we have the PVDF layer film for that sense of that materials. We have used the amplifier to amplify that low signals, and we use the output side that thing. So this is the with piezoelectric film for detecting the sliding force. We use the finger rubber skin on that, and how is the change in that physiological step, that you can see this diagram, that when we have to touch pressures, it will be give some signal on that time scale. So these are the applications of that sensors. Even that you can see that this is the human will wear their sensors on here, and it will be see on that display on devices here. So this is the integrated electrode type semiconductor polymer. On that we have the integrated electrode on that materials that is made of the chrome, gold, or any other metals. So this is the MEMS based electron sensors. So we use the N type the silicon here. Then we use the Si2 dielectric layer. Then we have again deposit the silicon here. And when this is the act as a switch, when we have to press on the switch, that it will be pressure and it will be contact with that silicon here. So it will make the some contact. So when it will be make the contact, it means it will be close. When will be it when we have to like that electrical switch, what is the working of electric switch, but same thing will be work here that. This is the another type of the touch screen set with a change in the capacitor. Here we have to check with the pressures here. So now we have to any doubt in that strain gauge or pressure sensors or tactile sensors, how that will be strain gauge and piezoelectric sensor will be work.
Got an idea now. It's okay.
So everything will be work on the pressures only, that or force something we have to apply it. So it will be either resistive type, inductive type, and capacitive type. So whatever the material we use, so either we use the inductor type of materials which change in the inductors. We can use the some two parallel plate here, Okay,
Okay.
and when we have to apply some pressures here on one plate, it will be change in the distance. So capacitor formula is equal to epsilon A upon D.
Mhm.
Okay, so distance will be changed, it means capacitance will be changed, area will be changed, it is a permittivity or dielectric constant. So between distance between two plates will be changed, the change in capacitance will be happen, we can say. So we can use the two parallel plate as a sensors, and like that one plate will be above and one plate will be above that. And there will be some dielectric material will be there, and we want to press that above plate with pressure, it change in the capacitance will, we can receive output side also that. Okay.
So, sir, one question is whether you have any magnetic sensor. I mean, for repelling or bonding magnetic sensors. No, piezo-magnetic or something like that.
Like that, it's depend upon like that, if you use some ferromagnetic or paramagnetic or ferroelectric materials will be there.
Okay.
Okay,
Uh,
so like that superconductor will be based on the magnetic material only that. So if
okay.
you use the superconductor, okay, like that,
Uh-huh.
some like that RF field you use, the radio frequency field you use.
Oh, okay. Uh-huh.
Okay, like that in the case of that when in the ISRO people are using that, are they, have you have you seen the MRI or that what is said by another that correct MRI and other things that
CT scan.
CT scan.
Yeah.
So MRI is what will be the, in the MRI we use the magnetic field.
Soft tissue.
What is the magnetic field value in the MRI?
Resonance imaging it is.
Yeah.
Sorry. Magnetic resonance imaging.
Yes, yes. So it is named, we use the magnetic field in that case.
Oh, okay. Uh-huh. They use the
So,
magnetic.
like that, people are said that like that people have the lab facility in which they have the MRI. So they advertise that we have the zero point 0.5 Tesla MRI,
Tesla.
1.5
Yeah, yeah. 1.5 to
1.5 Tesla MRI, 2.2 0.5 Tesla MRI.
what does that mean? Tesla is
Tesla
slices.
is the measure that unit of that magnetic field. Either
Okay.
we measure the magnetic field in a Tesla or Weber per meter square.
Oh, oh, oh. Okay.
Like that force we measure in the Newton.
Mm-hmm.
Okay.
Yeah. Okay.
So that is the unit of that, and that value is the zero point
Yeah.
0.5 Tesla that value.
Okay. Okay.
So I think that you are the in the field of that, like that in the your field that when your teeth will be that what you have to characterize that X-ray and what pion or POC, what will be said that.
IOPR, intraoral periapical
No,
radiographs.
no, no. Like that, you want to X-ray of that teeth from that above and upper both. That POV or
Orthopantograph.
huh?
OPG.
PVG or OPG?
OPG. Orthopantograph. It is.
Ah. So you use in that case what you use as a source for that?
As a source, same like normal X-ray
Yeah.
images.
Yes.
Radio.
That X-ray light will be move.
That is CBCT.
No,
Computed.
no. You like that the head will be put on some area, and there will be three or four X-ray ray and it will rotate.
That is CBCT. That is called CBCT. That is mm, cone beam, and uh, cone beam CT. Actually, it is
So
cone beam.
it
Is
will
there.
be
It
it
rotates.
has a
It
some, so it has some sensor. It will be detect some data
Yeah,
through the
yeah.
X-ray.
Yes, yes,
So
yes, yes.
okay. So when X-ray light will be the like that, this is the source and this is the detector. Your detector will be fixed.
Yeah, but it will be rotating around the head. Yeah.
Like that my head will be I put here like that. Okay, this is the detector. This detector will
Uh-huh.
be fixed and this is the source. Okay.
Source.
So,
Mm.
so what will happen? My source will be move and it light will be falls on my screen.
Mm-hmm. Mm.
Okay. So X-ray light will be falls on my screen. So you can see that when you see the teeth X-ray, some black dots or some will become on that. You can that there is a cavity or gap will be there.
Yes, 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 yes.
You can identify through that only.
Okay.
So
Uh-huh.
what will be they do? They measure that intensity of that X-ray. If
Oh,
that
oh, oh.
if the actual intensity will become means the teeth will become actually. Otherwise, it will be if the intensity will be there is a difference of the intensity of the X-ray or direction will be difference or some reflection will be take place. So it will be measured with the dark circle. Okay.
Okay, okay.
So
Uh-huh.
we have our engineer will what will do? It integrated that intensity in the form of the X-ray, and the signal will become in the dark and in the white form.
Mm-hmm.
So
Yeah, it
there will
is.
there will be one image sensor will be there. It will be collect that image of that teeth area that capture the image of whole the image of that our teeth like that my one upper teeth that last teeth will be like that my have the cavity. Okay.
Okay. Uh-huh.
So it have some gap or I have some sensitivity problem in my case that my
Okay.
teeth are more sensitive to cold and sweet. Okay,
Okay.
and
Uh-huh.
when I visit to doctors, he suggests me to you have to take out that teeth, that upper teeth. Okay,
Yes.
because
Okay.
we cannot refill that cavity
Uh-huh. Uh-huh.
because it will be
Wisdom
some
tooth.
band. He suggests me that he have some band in the teeth and we cannot refill that cavity. It is not possible.
Okay. It may be a wisdom tooth. Mm-hmm.
Wisdom teeth. Okay, okay.
Okay. Okay.
So
Mm-hmm.
he suggested me to you have to take out that teeth. There is no option to otherwise. We have converted like that. If we have below that, we have can refill that.
Yeah, yeah. You can see the X-ray and
Yes, yes. So he gave me that. He suggested me to some. I have some tested on that one. I take the upper X-ray and then like that you suggest me that CT. What is that character that lab test that he taken that.
PG.
Yeah.
Mm-hmm.
So according to that you can analyze it that this is the instrument only that.
Mm-hmm.
So these are the magnetic sensor will be also there because during the magnetic field the signal will be generated in the so your material should be in the form of the there the sensitive to magnetic only that property only.
Okay. How much that does this cost of if we do any sensor, if you want to do the sensor and actuator, how much the cost will be? How much that may? How much?
If you fabricated one sensor it will cost around 1 to 2 lakh rupees.
Oh, 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 oh.
If you
What?
it is a bulk if it is a bulk production then it cost will be reduced to around 40,000, 50,000. It is the quality and depend upon the company brand which brand you have to buy.
Okay. Uh-huh.
Because sensor have some property that it have the high accuracy, high resolutions, low error. Okay,
Mm-hmm.
people are working on that. Your sensor should be even sensitive to small pressure also that. Like
Okay.
that, we have to touch the mobile screen. If you only touch only with small pressure, it will be touch only that.
Okay.
Okay, and
Okay.
some mobile will become that if you press and press, even it will be not press in that case.
Oh, oh, oh. So even actuators, sensors and actuators together, if you want to create, like minimum it takes 1 to 2 lakhs or
Yeah.
more than that.
Yes, yes. And if
No,
you
no. Thing is, actually, our from our university, they have asked for the grants. Actually, so I need to apply for that
for what
regarding
for what
for my this thing study. So if at all,
you want to fabricate a sensor?
yeah, I need to fabricate sensor for my study. Actually, I need. I'll send you. You just let me know your mail ID. I'll send you the study and I'll send you one this thing also.
Okay, Kumar.
Actually, I proposed the study for to sense department earlier. They asked me to go through the in detail about the literature, but I
Okay,
couldn't. At that time, I couldn't do it. But recently, I got to know that someone had published the paper. It's similar to that of what I had proposed, which it was done in China.
okay.
So I got the article also regarding that. Just I'll send you, if at all, if you have any um, anything regarding any those study. If you have any idea regarding that, please let me know, because I just wanted some information regarding that.
Sure, doctor.
Can you just share your mail ID and number, sir?
This is my email ID, doctor.
Okay.
You can email on that paper and everything. And if you use the fabrication facility of Sense, then you have to ask more budget from your department.
That's what, because I'm not getting the exact this thing amount of how much to be.
No, because it is hit and tell case. You have to working around 3 to 4 years. Then you have to make that. You have to make 4 to 5 devices, and you have to calibrate their devices and which devices is working properly. You have to optimize your devices, and then you have to come to final version there.
I'll send you that study. Just let me know regarding that information, if you have anything regarding that and how much that may cost. I just
Sure,
let if
sure,
you. Huh? Okay.
sure,
Okay.
sure.
Thank you. Okay. Okay.
So this is the like that previously I have asked one question that what is the flexible substrate you use for that for biological tissue and detection of the biological sensors. So thin film depositions in case of that flexible substrate we use that like that. This is the spin coating system. This is the spin and this is the substrate, and we have to drop cast some solution or some materials which are the sensing we use as a sensing layer or active layer for sensing some tissue, biological tissue like that breast cancer cells or brain tumor cells or red blood cells or white blood cells we want to detect. So this is the heaters, this is the source, and this is the substrate, and we want to vapor that like that. This is the thermal systems. So here we have to put some materials, we have to heat that material, and it will evaporate on that substrate also. Or either we can use that spin coating system. Both technology we can use. This is the low cost technology, this is very high cost technology, and accuracy and uniformity will be in case of that physical vapor deposition is more in case of the spin coating system. So it will be easily and around that 1.5 lakh rupees instrument cost will be instrument, but it will cost around that 50 lakh rupees. So we use that solution processing of polymer semiconductor, vapor thermal evaporation right side. So these are the solution process and this is the vapor phase.
Okay.
So this is the solution processing step that we have to take during that. So like that we have to drop cast that some material on that, then we have to spin coat of that materials. There it will be circulate all the around area. This is the C is that the dye coating, dip coating. Like that, we have the some beaker. We have to fill that beaker with the some solutions, and we have to put our substrate on that beaker. That so this is a deep coating. So some material will be deposit on that substrate during the deep coating. Another third is the inkjet printing. So like that we have the printer, we have the inkjet printing, so it will be deposit on the substrate. So we have the we have to fill like that inkjet printer. We have some cartridge system like that. We have to fill our material on that, and where which is area we want to print, with that area we want to deposit through the inkjet printing also. So this is the drop cast materials of the film. So dropcast is the most reliable method for the thin film deposition from liquid solution. In this process, the solution is simply poured over the substrate, and eventual solvent evaporation from the recipient solution leads to formation of thin film of the solutions. So this is the actual diagram of the actual drop casting. This is the optical image. This is the schematic, and this is the uh, optical image of the drop cast. And this is the undyed solution, and this is the dye solution. So you can see that whatever the quality of the film, you can see that there is a textures in that thin film is there. There is no uniformity. Somewhere is a you can see that somewhere the quality of the film is textures and roughness is very high in case of the drop cast system, as we compare to that evaporation system, physical vapor deposition system or chemical vapor deposition system. But our material should be flexible, so people are mostly use the either drop cast, deep coating or inkjet printing in that case of the flexible substrate. So this is the step of the drop casting. So dropping of solution and spontaneous solvents evaporations. So we have to dropping here some solvent, and these are the we have to put on the hot plate of that materials, and because this is the form of the liquid, drop in the form of liquid. So like that, if we use the PDMMS or PVT or some organic materials or some like that inorganic materials, ZNO, magnesium oxide or some 2D materials if we use, so we make the solution of that material in the either in the acetone, IPA, isopropyl alcohol, toluene, ethanol, whatever the best soluble materials as per the materials properties, and then we put in the hot plate and we have to evaporate that liquid at acetone or IPA, and this will be evaporate, and only the dry layers will be remain on the substrate on that in that case. So this is the dye layer. After that evaporation, this will be dye layer we have to obtain. So this is the spin coating diagram. This is the spin coating systems we use, and generally involve the formation of the thin film with the thickness varying from few nanometer to few micron uniformly on the substrate by dispersing the solution of the desired material and rotating it on the high speed varying to 200 to 4000 rpm. So what will be happen? We have to take the some substrate and we have to drop cast some materials. Suppose that we want the thickness of around 100 micrometer or 100 nanometer. So we have to optimize that spin coating speed, timing and RPM of that spin coating. If we require the high thickness, we keep the RPM is the low. If we require the thinner of that, then we keep the RPM is the high in that case, and we can rotate for that some 30 second or 60 second. If we require the thickness is high, we rotate for the 3 minute or 4 minute, and uniformity in case of that spin coating is more as compared to the drop cast in that case or deep coating. So this is the spin coating systems. So dropping on the spanning substrate, we have to through the micro pipette we have to drop 3 to 2 drop, or what is the thickness you have to require. If you require the more thickness, you can drop more drop on that substrate, 4 to 5 drop or 20 microliter or 40 microliter, 100 microliter solution you can drop cast on your substrate. Film thickness depend upon many controllable parameter like dW by dTt, Wt solution, viscosity of that materials. So this is the rotation speed of that materials. This is the RPM, and this is the timing, solution viscosity, how much the solution will be viscous. It will be high viscous or less viscous. It depend upon that film thickness. Advantage: uniformity, control on the thickness, reproducibility. We can produce the same thickness or same parameter again and again on the same substrate. It will be not change in that case. But in case of the physical vapor deposition systems, some variation will be happen like that. Suppose that if I keep the same parameter for the 4 to 5 substrate, maybe that 5 to 10 nanometer difference in the thickness we can obtain in case of the physical vapor deposition system. Disadvantage is the waste of the material, no large area, film desired dry fast, no time for molecular ordering. So these are the all the on the large scale we can drop like that. We want on the 2-inch vapor we want to fabricate the sensors on the 2-inch vapor array of that 100 array of the sensor we can 2-inch vapor. Through that spin coating it is not possible because uniformity is very less in that case of that 2-inch vapor. So in that case we use that e-beam evaporations or ALD or MOCVD in that case for the deposition of the large area sensors. So this is the diagram of the spin coating speed. So this is the rotator. We can put here our substrate like that. These are the 2-inch wafer we have to put on that holder. So these are the spin coating film thickness. So this is the rotation speed, film dominated, evaporation of the diminutions. So this is the most commonly reported explanation between the thickness and rotation speed. This formula you can calculate how much the thickness will be calculated. So COD the concentrations, viscosity and liquid density of that materials. So through that you can measure that how much the thickness or final thickness you have to obtain. Theoretically you can calculate. This is the spin coating. So solution is made in a volatile solvent by mixing the material and the solvent and stirring for the few hours. So in the sonicators, we mix the solution, make the solvent. So you that like that if you the use the Jadeno can be dissolved in the ethanol, DI water, or IPA or acetone. So you mix that Jadeno in the and stir for the 3 to 4 hours to make that soluble that solution in that case. The rotation of the substrate enable uniform spreading of that adequate amount of the solution and splitting of the excess solution of the substrate. A rapid airflow dry the majority of the solvent and provide uniformity to the deposit layer by leaving just the molecules of the material of the substrate. So you can dry with the dry nitrogens or argon, and some water molecules will remain. So you can heat in that case also that in the hot plate. So thickness of the film of the material depend on the several factor of the solutions: solvent, boiling point, solution viscosity, material solubility in the solvent, material concentrations. So the main advantage of the spin coating include quick and easy protection of the highly uniform film. So these are the thin film depositions of that spin coating system. You see the another is the doctor blading is the another technique through which you can deposit the thin film. So through the blade, so that like that you have the one blade, you can drop cast and you can that you can put blade and uniformity like that. This blade will be move here. You see the bar coating methods. This is the deep coating. You hold your substrate in the solutions. So this is the thickness control. Lagmar blowjet is the transfer of Lagmar film to substrate. That how can you control that thickness of that film? So this is the plot. So I think that this is not. So how you make that when you have to deposit everything on that you have to drop cast, or you can use the spin coat or blade or other technique to deposit your metal film. Now you have to use that on the flexible substrate you make two devices. Like that if you want to make that transistors, diode or memory devices, anything you want to add sensors. So for that you have to deposit some pad on that source drain or gate you want to fabricate it on that sensing layers. So you can patterning your devices through the shadow masking, through the thermal evaporation, photolithography, photo patterning, soft lithography, nano technology, physical demolition, atomic force nanolithography. You can use any technique to deposit to transfer of the pattern on thing. So this is the shadow masking plus skin plating spray analysis. Okay. So this is the mask you have to use. This is the substrate, and now there's you see that this is the screen. This is the pen substrate. So these are the design on the mask. This design you have to transfer on the substrate here. This design. So you have to spray that gold, chrome or whatever the screen on that your paste is that spray, and you transfer that this spray will be sprayed here only this form. So you can more for that. You can visit this paper also, that for how they have to transfer that things that. This is the shadow mask plus selective wettability of diagram. Like that, this is a silicon wafer with a 300 meter of the silicon oxide layer on that substrate. Uh, this is the hydrophobic SAM self assembled monolayer. This is the metal mask. So this is the opening of that metal mask here. So these are the two that P dot PS is conductive polymers. You have to deposit. P dot PDS is the conductive materials. So on these palaces you have to deposit these conductive materials. UV lighted damage ODS film, you can see that. So shadow masking, you can transfer the electrode. That previous class I have used that shadow mask through the thermal pressure, use the lithography both technique. So this is the photo patterning, that whatever the you use that same you can use in the flexible substrate. So same principal equation of standard photolithography. Resist is the active material. So this is the active material. Use the positive of photoresist. That UV light you transfer this mask here. So this pattern will be transferred on your, after etching these things will be remain. So this is either made of the aluminum, chrome, nickel. This is the conductive materials, that metals are there. So example, patterning of the pixel in the OLED display, patterning of the whole transport layer. So 5 micrometer of the size, the distance between two these is around 5 micrometers. So you can transfer the channel length between the two electrodes should be the 5 micrometer. You can transfer through the photolithography. This is the soft photolithography. Printing material has to be added to the substrate while the interaction with the mold has to be minimum. So soft means that substrate and that printing materials have the interaction is the less. Otherwise, it will be maybe the chemically interact and it will change the property. So during the photoresist should be not interact with the conductive polymers, semiconductor polymers. So use that photoresist that are less chemically interact with that layers. So use the, in that case, use the soft photolithography. So micro contact printing, that in the micrometer you can design. So use the PDMS layers here. So this is the silicons, there is a U, and you above that use the PDMS layers. So these are type of the structure you have to obtain in that case. So this is the fabrication methods, that steps you have to taken during the soft lithography. This is another technology, micro printing technology. This is the nano imprint lithography, NIL, embossing. So this is the mask, that master mask, and you have to contact with that this mask with it with target oligomer, and you have touch with that, and then you have to expose with that. There are two room temperatures and hot imaging with that. You have to heating that substrate in around 300 degrees Celsius, 400 degrees Celsius to stuffing that substrate on that design on the substrate. This is the physical delaminations. I have not more idea about that because I have not used that technology. This is the atomic force nanolithography. So you use the one small tip to write that patterns, and it will be write dot by dot. So like that, this is the tip, and this will be write your image here. This will be patterning your electrode. So this is the schematic diagram of that. You can read what more about this references I have given you. So again is the non-soluble materials. This is the just evaporation technology. This is the thermal evaporations. This is the diagram of the thermal evaporations we use for deposition of the materials, aluminum, gold, chrome, or whatever requirement of materials. So after the deposition, this is the AFM image, atomic force micro image, image of that materials. So next is the one that design and fabrication of the flexible MEMS-based electromechanical sensor array for breast cancer diagnosis. Till now, if you have any doubt regarding flexibles, photolithography, you can ask me. If you have any doubt.
No, it's okay.
So what will be in these papers that people will be use, that they use the MEMS technology to detect that breast cancer diagnosis. So they analysis the electrical characterization of the tissue specimen, that breast tissue, have the feasibility of using the sensor for mechanical characterization of the tissue specimen. So they use the 8 strain gauge sensor. Actually, they use in this they use design the strain gauge sensor, acting as a mechanical sensors. So it will be converted that mechanical force into electrical signal, that resistance sensor. Using they use the poly, that 3,4 ethylene dioxophene poly, and P dot PSS as a conductive polymer on the polydimethylsilane PDMS as the substrate. So they use the PDMS as a substrate and P dot and PSS as a conductive layers. So 8 electrical sensors were fabricated using that SU8 pillar on the gold. So they use the SU8 as a photoresist. On that they have deposited gold, and they use that 8. They have like that. This is the substrate, and they use the 8 pillars. 1, 2, 3, 4, 5, 6, 7. Like that, eight array of the sensor they have fabricated on SU8 type pillars, and these are made of the gold AU. Okay, and here on PDMSs, this is the PDMS. On above, they have used one SiO2 layers as insulators. So these are the 8 pads. They have contact pads for the strain gauge. See that these gold pads. These are the 8 strips they have fabricated. You can see that how much the small pad size, and these are the contact with the tissue. These are centrally that, and these are the PDMS layers, and this is optical image of that. Okay, and this is the fabrication of the process. So this is the silicon layers, basic silicon wafer. Above that they use the PDMS layer they have deposit. On above that they have deposit that gold. So gold they have deposit through the thermal evaporation or e-beam evaporation system. And then these are the masks they have used, and after that developing this type of structure they have fabricated. Okay, then above that that's 8 pillar they have deposited one insulator outside SiO2 through the oxidation. So either you deposit SiO2 through that silicon as a substrate and oxygen as a source material using the RF splitting system, physical deposition, or one oxidation furnace will come. So you deposit a 3 to 400 or 30 to 40 nanometer of that oxidation layer for the as insulators, and then you have to remove this above that gold plate, this oxygen that using the KO solutions or some solvent that remove that, use that layers to remove, and again that you have to deposit one gold layer here to make the contact sorting of that material layers, and then you use the SU8, and after that patterning you have to see that this is the final devices of your strain gauge sensors. So these are between that, these are black are that P dot or PSS. So these are the conductive layers. So between these we have to, when we have to connect it, these electrodes through the some source meters or some supply. So you have one source meters here. Uh, I can show you that. second. So these are the like that. This is the source meters for electrical characterization. You use these source meters. Then
Mhm.
this is the probe stations. Like that, this is the devices I have made. So you have to take contact. You can see that these are the pairs. This is the real design of devices.
Okay.
So you have to make the gold. This is made from the shadow mask. I use the shadow mask, not a lithography. You have make the devices like that. You can see that this is the integrated electron of the devices. So this type of the sensors you have to fabricate it. So this is a gold pill. Take the electrical contact on below some conductive layer will be here on that. So you have to use that type of system for the electrical characterizations, like that when I have to drop cast here some like that in between there and some tissue here, some biological tissue I have to drop cast, and then I measure the resistance or electrical current between that, how much the current before that tissue I have to drop cast, and after the tissue, and check that how much the change in the current or resistance value I have to measure through that.
Which technique is followed? This
Yeah,
which technique is followed to do the sensors here in this method?
which technique means?
No, a method to fabricate the sensor. This
Actually,
is
I
the
use like the silicon vapor I use SiSi tool.
silicon paper. Okay,
Yes,
same what is on the screen.
yes,
Same.
yes, yes. Okay.
Okay. Uh-huh.
And then I have taken that. I have made that deposit some materials, that semiconductor materials through the CVD or the RF splitting, that whatever the facility you have used, that fabrication. And then
Okay.
about that you use the shadow mask. That ID pattern is I have already prefabricated shadow mask here, and
Okay.
I put that my silicon layer on that shadow mask, and then I put the gold chrome on through that. So some thermal
Okay.
evaporation technology.
Okay. Okay. Uh-huh.
And this type of the pattern that you see, that gold pattern will be there use that ID pattern in the resulted. Okay.
Uh-huh. Okay.
So you have to that characterization. You need the source meters.
Mm-hmm. Mm-hmm. Okay.
So this is the sensor fabrication SAM images. SAM is another technology, that scanning electron microscopy, that will be give you the image in the nanometer, that high scale high resolution image of your devices. If you cannot see your from that your eye or through optical microscope, use the same technology. Through that you can check that what is, so you check that how much they have fabricated devices. That these are the that instant case sensor they have fabricated.
Mhm.
Okay.
Okay.
So this is the eight paired circular pairs. See, one, two, three, four, five, six, seven, eight. Hmm?
SU is meant for what do you mean by SU?
SU eight.
No, SU8 is okay. Full form of SU is
SU full form.
so,
Some materials name should be there.
okay.
1 minute, I will let you know. There's some organic materials named that epoxy type
O-
based organic materials. I have not.
Okay. Uh-huh.
I will next
Fine.
class I will let you know that.
Okay, fine. No problem.
So this is the same image of the actual devices they have fabricated. That previously I have seen that schematic. See that how much image will we see you.
Uh-huh.
So this is the actual devices. A photo of the flexible MEM sensor. That's on PDMFs. They have fabricated that.
Oh, oh, oh.
So it will be if you bend, it will be remain the same form, flex and move and here and there. So these are the 8 devices you have on that 8 things.
Okay.
So this is the force that that how you measure that working mechanism of that things. So see that this is the Stern gauge. These are the 8 Stern gauge you have taken. This is the PDMS layer. This is the input resistant.
Okay.
Okay, and this RS is that change in the resistant. So you can see that when you have to not to apply any force on that pillars, and when you apply the some force, so change in resistance that you can check that GE is where E R A and R is the this epsilon naught is that strength, R is the initial resistance of the sensor, and RS is the sensor resistance on curved surface. When we have to put the pressures or force on that, but after changing that resistance, after that applied some force on sensor, whatever the resistance value change due to the force will be denoted by the RS. So this is the change in resistance we have to calculate through that, and this is the strength we have to calculate that through the T beta 2R. So T is the thickness of the film and R is the radius of the curvature through the bending. When we have to bending like that, this is the my PDMS substrate of sensors. I have to bend this like that on my this finger. I have to bend these sensors. Okay. Now, I will take that radius of that my finger, how much the bending of radius I will take, and I will calculate the strength of that sensors. How much the change in strength will be take place after the bending.
Mhm.
Okay.
Okay.
So this is the schematic of the diagram. I will bend through that on that circular that cylinders. Okay. And I will take that during the after the bending, I will take that value of the resistance. Here, see that. This is the 3D printer cylinder. Here I will do bending. I will take the contact from here, data card, and I, in the sensor and in the calculator on that software, I have calculated the change in resistance here in the form of the resistant. So this is the same of the microgrid, and after that breast cancer cells. Okay, this is the cell I have drop cast on that materials.
Mhm.
So see that this is the images of that breast cancers A and B.
Yeah.
ठीक है?
Okay.
One So this is the device mounted on cone shape holder for mechanical and electrical characterization of that actual photograph. That this is the probe stations they have used. Through the probe they have measured that resistance. These wires are coming through the probe, that optical microscope here. So you take easily contact through the pad, and then you have to there is a mechanical system where you have to flex that substrate also, round, square, or whatever the form you want to bend that substrate. And after the bending, what is the change in the resistance, you can measure that, how much the strain will be produced, stress will be produced. And you can check after the tissue will be applied on after bending and before bending, that how much the change in resistance and strain will be produced. You can calculate through that measure the setup. So for measurement you need the one probe station with the high resolution of the optical microscope, and you need the one electrical characterization, one source meter. So this is the that position, that bending of that thin film, that zero, the radius before that 0, 2, 4, 6 micrometer, 8, 10. This is the bending of the sensor they have measured, and sensor voltage. So you can check that how much that voltage will be changed with the bending, that you can check. Before bending that 2.5 volt, and after that 60 micrometer bending, you can check that how much the voltage will be decreased in that case. And this is the mechanical characterizations. After the being here, you have to apply the cancer tissue here. You apply the cancer tissue here. So sensor 1, sensor 1 beginning, this is the beginning, that base resistance of the devices. Without that cancer cells, when you have applied here the cancer cell, the resistance will be changed here. Your voltage, sensor voltage will be decreased in that case. With specifically bending, you can check that. And this is the force that you have to apply, that mechanical force. So there is a no force before your tissue, that is a zero with the bending. When you apply some cancer tissue, some force will be applied on that case, some change in the force, that drop cast weight, how much the drop cast you have to apply, that will be checked with the force, that mechanical force, that on that case. So this is the cancerous tissue here. This is the beginning of the tissue, beginning binging tissue. So you can check that there is no cancer tissue will be there for sensor 1, 2, 3, 4, 6, 7, 8. These are all the sensors are fabricated. This is the 8 sensor you have to fabricate, that 8 Eastern gauge sensors, and this is the performance, that parameters of the 8 sensors. That now this is the 3D inventor software for design of that MEMS based sensors of the beginning. So from Autodesk, you can go to the Autodesk, and you can download the Inventor 3D model softwares, and you have to log in through that through student version of your account in the system, and you can design your own design, 3D design. And in this you can because your system will be mechanical, electromechanical system. So system should be the mechanical, but it will be perform the electrical form, that output would be in the form of the electrical system. That's why the name of the MEMS will be. So it will a combination of the mechanical, electromechanical system. Working principle should be based on the mechanical system. So you have to apply the force. Force should be in the form of the mechanical form. It is pressures. It is also in the mechanical form, but output should be in the form of the electrical. So this is the Autodesk inverter. So you can after that login and design, you can use that, open the design, that or new can design, you can use the new project, that whatever you want to create, you can create through that system. Then this is the template. You can open that previously already installed template in that design. This is the pivot bracket. You can this is the part 0, part 1. These are all the template. You can create your own template, your design, like that. Sensors, Eastern gauge sensors. So you click on new, type your file name, save with the Eastern gauge, and you can save it in your project. And then the working window will be open, and you can design your Eastern gauge sensor here. So it is just for the example, for your understanding. I will take your that pivot bracket design. You will open that. This is the pivot bracket design. This will be open to the pivot bracket design. So this is the all the execute, resolve, lob, sweep, rip, hold, field, sample, cell, draft. These are all the options of the design. You can take patterns, surface, whatever the plastic part you can take, hammers, take work features, whatever the plan you required, you can take according to your design that. So this is how to explore that exacting design. So this is the redo, save, new, open. These are all the window will be available on that here. So this is the tool on the navigator bar to have the control of view and orientation of that your signal layers. This is the toolbar that steering wheel, pan, zoom all, freeboard, view face, navigation bar window will be available here. This is the product that standard MMPPT, sheet metals, which project you matrix you want to use that you can use that. This is the working window. So this is the that design of that pivot bracket design, XYZ direction. At what angle you want to cut, where is spaces. This is the mechanical people are using their design of the bearing and shaft and that during robotics design they have used for that Autodesk Inventor 3D model system. So mechanical people are more expert in that Autodesk as compared to electrical electronics engineers. But you can try your design through the software also that if you are. So you can draw your sketch like the pencil and you can put your measurement double clicking here and you can put your dimension here also that. So they use the extrude on that surface that how that see that. Now they use that hexagonal structures above that. Check that they have put the dimensions, distance where you want to put that things. Again they have the circular things here. Cylinder they have to put here to cut on that things. To cut the cone. So you can use any component radius. So you want to add that plane and everything that you can use that. How to cut that plane. How to create a ribs in the solid. This is the ribs they have to create it, these ribs. See that. So in the Autodesk you can design your MEMS based design here. So these are all are the snapshot of that inventor tools for 3D modeling. You can view the side view, front view, top view of that your design also that. See that this is the final 3D design of that your device. So this is hexagonal they cut, rectangle they cut, cone they have to made, everything they have to made and they inserted on that images. So you can design your instant gauge sensor here also that in case MEMS base, actuator here also that. This is the interaction of the two solid. This is the another examples. These all are that to measure the dimension of the 3D design. Anything else? This is from my side. Anything you want to ask, discuss?
No, I'm fine with this. This Auto Disk, it is available in. It is free. This thing or
Yeah. This is free. They have shared one link that you can access my PPT, my video. Even we have to upload that YouTube link also there. That
Okay. Uh-huh.
okay. So you can
Okay.
access the PPT through my Google Drive folder also. It is open for everyone. That I have given the access to everyone. You can download and you can read that PPT.
How to do that? You have
Yeah.
no how to open this thing.
One thing.
Okay. Mhm.
So here one that they have provide you like that.
Yeah,
Uh,
I got this actually. Yes.
I think if you go there, problem solving session here.
Okay. Uh-huh.
See that here. You see the lecture. This is the drive link that.
Okay. Fine. Uh-huh.
Okay.
Okay.
This is above is my and below is Arpita that taken on Tuesday class that.
Okay. Mhm.
So they are the two TAs who are taking that your class. So till 10 I have uploaded. This is the YouTube link. This is
Okay.
the backup drive and this is the that drive of that your PPT that.
Okay. Fine.
So
Fine.
you can click that presentation folder link and backup video link. You can click that. Which video you want to see that. You can subscribe my channel also. Like that.
Okay.
This is my YouTube channels. If you
Uh-huh.
go to that, this is the my channels.
Okay.
So this is the week 4 lessons.
Mm-hmm.
So this is my channel
Good
name
evening,
Ashok
everyone.
Kumar. That
This is
P19EE203.
Ashok Kumar,
If you search on the
Payment
Google,
Scholar
YouTube, that you can. So you
from
got the
IIT
all the
Kharagpur.
video that in sensor and
And
etc. That
today
everything.
we have the live
Okay.
session
Fine.
class
Fine.
4
Thank you.
Okay.
for week 4 of that
Thank you.
sensor and external V class.
Anything else?
No, just I wanted to clarify this. My study I'll be sending. Please let me know about that.
Sure,
If
sure,
any.
sure. That
Yeah.
that will help you.
Okay. Thank you. Thank you.
Okay.
Okay. And how about this? If any exam to be written, any.
No, you have to. They have circulated one form too for that
Yeah,
fill up.
yeah. That we had done actually. We have not got the hall ticket or anything like that.
It will be maybe released on that after 24 or maybe that. It will be on 29 April,
Yeah, 30th.
30,
30th April.
30 April.
Mm-hmm. Mm.
Exam that whole ticket may be released on that after 20 that.
After 20. Okay.
Exam format should be type of example will be in the list. See that.
It's a computer based
Yes,
online.
yes. And it will be notified through that whole ticket will yet to be released. They will notify through the SMS and through the email.
Okay, okay.
And you have to you have to given that link how to you appear on the on screen calculator will be available for you. You
Mm-hmm.
have not to carry the calculator through the online examination. You have to that through like that GATE exam. Online calculator will be available, so you have to practice that also. That assessment link you have to given to that. In announcement, they have put one exam format of April to 2023.
Mm-hmm.
So you can go through that also. That
Okay.
uh, the question will be on the computer and the answer will have to enter on the computer type of question. may include multiple choice question, fill in the blanks, or essay type answer. So even you have to write some 2 to 3 line of that questions also that.
Okay. Mhm.
Like that, they ask you that what is the working principle of that piezo resistance or difference between piezo resist or piezoelectric sensor. So you write
Oh,
that 2 to 3 lines also that, or some fill in the blanks type, or some true false type, or multiple type choice question will be there.
okay. Mhm.
Okay. So maybe they have send you one email regarding that also. You have got any email regarding that
Yeah,
format
yeah,
also?
yeah. Yes, yes, yes. I got it. I got it.
So date of exam is the 30th April, and your hall ticket will be 2 week to the prior to exam date. Maybe you have to after that 20 you got the hall ticket.
Okay, fine.
Okay. Anything else?
No, thank you.
Okay. Then we meet on next Monday.
Okay.
Okay.
No, thank
Okay. Okay. Thank you.